Random cards. Number 1. Overall approach to use of integrating factors for differential equations. This process applies only to ordinary first-order differential equations. First, the equation must be in the form y prime plus a of x times y equals b of x, where a of x and b of x are functions of x. Once the equation is in this form, we construct the integrating factor, e to the power of the integral of a of x dx. We then multiply both sides of our first-order differential equation by the integrating factor, e to the power of the integral of a of x dx. This will give the derivative of the product of the integrating factor times y, equal to the integrating factor times b of x. We will then be able to integrate both sides to get y times the integrating factor equals the integral of the product of the integrating factor and b of x dx, and solve. The take-home point is that the first-order differential equation must be in the form y prime plus a of xy equals b of x, and the integrating factor is e to the power of the integral a of x dx. And finally, that multiplication by both sides will, on the left-hand side, give the product of the integrating factor times y, all first derivative. Vector decomposition. Given a vector in the plane at some angle with an absolute value of magnitude of v, the component in the x-axis will be v cosine theta, and the component in the y-axis will be v sine theta. The vector v can be expressed as the component v sub x times I plus the component v sub y times j for a vector in the plane, where I and j are unit vectors. Natural selection is not teleonomic. Natural selection alone cannot have a goal. It cannot drive a population from a local maximum to a higher maximum. But natural selection plus genetic drift, or more generally, genetic fluctuations in populations, can and will drive a population from a local max to a higher max. Phase space defined. The phase space is a mathematical concept, an abstract space where each point represents a unique state of the system, defined by all its relevant variables. Phase space trajectories. A phase space allows us to visualize the evolution of the system in time. As the system changes, its representative point in phase space traces out a trajectory. This trajectory documents the history of the system, its evolution from one state to another. Coordinates of phase space. we have generalized coordinates and generalized momenta in phase space. The generalized coordinates q describe the configuration of the system. For example, theta for a simple pendulum or xyz for a particle. Generalized momenta, p, are the variables related to motion of the system. They are defined as p equals the partial of L by the partial of Q, where L is the Lagrangian. For a simple particle, P just equals mv. Dimensions of phase space. The dimension of a phase space is twice the degrees of freedom. For example, a single particle moving in one dimension has 1 degree of freedom. So its phase space is 2D, with coordinates x, p sub x. A simple pendulum's phase space is also two-dimensional. A function of theta and p sub theta. For an example, consider the phase space for a simple harmonic oscillator. For a simple harmonic oscillator, like a mass on a spring, the position is x, that's our q, and the momentum is p equals mv. For energy, E equals p squared over 2m plus 1/2 kx squared. But the total energy is conserved. So the equation must describe a closed curve. In fact, if we rearrange it, we will get x squared divided by the square root of te divided by k squared plus p squared divided by 2me squared equals 1, which is the equation of an ellipse. Each point on the ellipse equals a unique state of the oscillator with the same total energy. Applications of phase space. In classical mechanics, the phase space is the geometric framework for understanding the evolution of Hamiltonian systems. In statistical mechanics, phase space helps us understand systems of many particles. A phase space volume is crucial for calculating thermodynamic properties like entropy. In quantum mechanics, not so much, because of the Heisenberg uncertainty principle. But there are related concepts like the Wigner quasi-probability distribution that serve as quantum analogs of the phase space. Discuss redshift and the problem. The redshift, z, equals the change in wavelength divided by the wavelength, which equals the difference between the observed and emitted wavelength divided by the emitted wavelength, which for electromagnetic radiation is basically equal to V divided by C. The problem is that for large redshifts, the resultant velocity is much greater than C. So if redshift Z equals V over C, then V equals Z times C, and Z is greater than C for all Z greater than 1. But of course, it's not the source that's being redshifted. It's the photons. The four pillars of logical positivism. 1. Verificationism. Metaphysical propositions have no cognitive significance. 2. The analytic-synthetic distinction. There are only two types of meaningful statements: analytic and synthetic, which roughly correspond to Hume's relations of ideas and matters of fact. 3. The unity of science, at least in principle, which entails some degree of reductionism. And 4. The rejection of metaphysics. Eigenvectors and eigenvalue. An eigenvector will satisfy the equation AV equals lambda V, where A is a matrix, V is the eigenvector, and lambda is the eigenvalue, a scalar. Again, AV equals lambda V, where A is a matrix, V is the eigenvector, and lambda is the eigenvalue, a scalar. An eigenvector undergoes scaling, but not rotation. A substance decays over time. Let's write and solve the differential equation. In simplest form, the differential equation for the decay of a substance is dy by dt equals negative ky, where y is the concentration of the substance. Dy by dt equals negative ky. Therefore, dy equals negative ky dt. Separating variables, we get 1 over y dy equals negative k dt. Integrating both sides, we get the integral of 1 over y dy equals negative k times the integral dt. Integration yields the equation natural log of y equals negative kt plus c. Exponentiating both sides, we get e to the natural log of y equals e to the negative kt plus c. Thus, y equals e to the negative kt plus c, which is equal to e to the negative kt times e to the c. And if we let e to the c equal c, then we have our solution y equals c times e to the negative kt. The Galilean transformation. We have two reference frames, f and f prime. At t equals 0, they are superimposed at the same origin, but f moves to the right at v much less than c. At t2, an event occurs at x prime, y prime, z prime on f prime. What will be the coordinates of the event on f? Again, f prime moves right at v much less than c. At t2, an event occurs at x prime, y prime, z prime on f prime. The coordinates of the event on f are x prime equals x minus vt sub 2, x equals x prime plus vt sub 2, y equals y prime, and z equals z prime. What is pKa? pKa is the negative log of the acid dissociation constant, or Ka, and measures the strength of an acid. Unlike pH, which measures the acidity of a solution, pKa is an inherent property of a molecule that indicates how readily it will donate protons. A low pKa corresponds to a strong acid. Thus, the pKa of hydrochloric acid is negative 9.3. A high pKa indicates a weak acid. For example, the pKa of acetic acid is 4.76, and the pKa of water is 15. Buffer region. When the pH of a solution is equal to the pKa of the acid, then the concentration of HA equals the concentration of A minus. This is the point of maximum buffering capacity. When the pH is less than the pKa, the solution is more acidic than the molecule, so HA dominates. Dissociated proton and base will tend to combine to form HA. If the pH is greater than the pKa, then the solution is more basic, and so the unconjugated base dominates. HA will tend to dissociate into proton and A minus. What is the formal relationship between pH and pKa? The relationship depends on the concentration of the base and the concentration of HA. pH equals pKa plus the log of the quotient of A minus divided by HA. In summary, pKa is for a specific molecule, while the pH is for a specific solution. The pKa ranges from negative to 0 to large positive, whereas the pH ranges from 0 to 14 in aqueous. The pKa is a constant value, not affected by the concentration of the species, whereas the pH depends entirely on the concentration of the species. The pKa is just a measure of how much HA wants to dissociate to form proton plus A, whereas the pH is just a measure of the hydrogen ion concentration of the solution. The Gibbs free energy and work. Recall that G equals H minus Ts for any process of constant temperature. Differentiating, we get dg equals dH minus d of Ts, which equals dH minus TdS because temperature is constant. So we get dg equals dH minus TdS. From the definition of enthalpy, we get dg equals du plus d of PV minus TdS. And at constant pressure, we get dg equals du plus PdV minus TdS. Now, we can take the internal energy and apply the first law for a reversible process. But because g is a stable function, it doesn't matter. And we get dg equals squiggly dq plus w plus pdv minus TdS. Now, we need to consider the w. There are many kinds of non-expansion work: biochemical, electrical, surface, and so on. We know how to handle expansion work and call the non-expansion work dw prime reversible, dw prime rev. And so we get dg equals squiggly dq plus dw reversible plus dw prime reversible plus pdv minus TdS, where dw reversible plus dw prime reversible equals the total work extractable from the process. But dw reversible equals negative pdv, so the pdv's cancel, and we are left with dg equals squiggly dq reversible plus dw prime reversible minus TdS. Actually, because q is reversible, these are probably not squiggly dq's. So we're left with dg equals dq reversible plus dw prime reversible minus TdS. Now we know that dg equals dq reversible plus dw prime reversible minus TdS, but ds equals dq reversible divided by T. That's the Clausius entropy. So dq reversible equals TdS. Therefore, dg equals TdS plus dw prime reversible minus TdS, and so dg equals dw prime reversible. So it turns out that Gibbs equals the max non-expansion work that can be extracted from the system. So we have dg equals dw max reversible. If we integrate, we get g, or delta g. But remember, one of the key properties of a reversible process is that they yield the maximum work. So the integral of dg equals the integral of dw prime reversible, which yields delta g equals w prime max. In other words, the delta G is the total non-expansion work that is available from the system.